Thank you for joining us today as we discuss the availability of potable water in impoverished communities worldwide.
One of the most important parts of a project is to define the problem. In this case, the problem is the difficulty and inconsistencies that people across the world face when trying to access potable water. The consumption of contaminated water is the second highest cause of death in lower income countries, and statistically rural communities in Africa are the most in need. Coastal communities suffering from a lack of water have a virtually unlimited source of water beside them, but can't take advantage of it as desalination has historically been expensive and impractical. This inability to have a consistent source of potable water causes numerous issues for communities, including social issues such as health, economic issues such as low growth, and environmental issues such as abandoned infrastructure. These issues all stem from this problem of water inaccessibility. Due to the vastness of the problem presented, a case study was performed on the community of Foundiougne, Senegal, in Africa. Foundiougne is a small community of 7,000 just inland of the Atlantic Ocean on the west coast of Africa. Foundiougne is on the Saloum River, a unique river due to it carrying brackish water. Brackish water is a mix of saline and fresh water, and in the case of the Saloum River, it is due to the climate and the low flow of the river that the water is brackish. The infiltration of this brackish river water also causes the regional aquifer to have saline water, and therefore the groundwater is salty. The context of this case study is based upon the specific conditions of Foundiougne. This includes the water quality and climate, existing infrastructure, as well as accessibility to energy, gas, and outside assistance. The regulations and guidelines that were used were selected to satisfy the requirements of the Senegalese government. However, as the government of Senegal has little published in regards to water regulations, the World Health Organization, or WHO, guidelines were primarily used.
As with any engineering project, there are a number of constraints that must be addressed. The system must be able to supply 11,000 residents with clean, potable drinking water. It must be able to withstand the hostile climate of the Sub-Sahara and any future climate changes. The water must meet the World Health Organization's water quality standards. It must appropriately dispose of the sludge, brine, and waste. The system must be capable of operating for 15 to 20 years, and effluent salt concentrations must not exceed 200 milligrams per liter. Due to the general nature of the project, the overall goal with our criteria was to minimize as much as possible. This goes for the electricity and energy usage, the use of chemical additives, the capital and operating costs, the amount of operation and maintenance required, the physical footprint of the unit, and finally the interruptions in water service to the community.
With the problem at hand clearly defined, three essential stages were considered for the design process. The first of these was determining the most suitable source of water. The second was, if necessary, comparing the water quality to the World Health Organization drinking water standards. The third was designing a sequence of treatment processes that would provide potable water for the community. Foundioune's location next to the Saloum River and its situation above the continental terminal aquifer provide the opportunities to extract groundwater and river water as sources of raw water for treatment. Unfortunately, the low flow of the river and surplus of evaporation have led to the salination of the Saloum River. Furthermore, river water penetrates the underlying aquifer, so surface water and groundwater resources in the direct vicinity of Foundiougne are contaminated with elevated levels of sodium, chloride, and other ions. The decision was made to consider extraction of groundwater at a location farther southwest of Foundiougne, where the salinity of the groundwater is far lower. A third option was considered, which involved the construction of a transmission line from Kaolack, a city located about 60 kilometers east. Although this option would not involve any treatment processes, the water would need to be purchased from Kaolack, and Foundiougne would not have any control over its supply.
The raw water quality of the surface water and the groundwater source locations are presented in this table. It is important to consider source water quality when determining which solution to utilize, because the treatment processes are entirely dependent on the influent water quality parameters. The readings higher than the provided guidelines are denoted in red, and it is clear that the salt and turbidity values for both water sources are above the guidelines. The first design matrix was made to provide the best solution strategy to the problem at hand. It weighed the options of status quo, which meant shipping water into Foundiougne, building a transmission pipeline from the nearest water treatment plant, treating surface water, and treating groundwater. A variety of relevant criteria are listed to compare each solution, and each solution's rating is based upon an evaluation scale. The primary criteria used to weigh these solutions was the costs, both capital and annual. The cost weighting was half of the total criterion weighting and was determined using cost estimations for each potential solution. The two most likely solutions to be provided by the matrix were the treatment of groundwater or surface water, as the costs associated with the other two options were too great, both initially and over the long term. The main deciding factor between treating surface and groundwater were the capital costs, as groundwater is usually preferred to surface water because of the pretreatment provided by the soil as the water infiltrates through the aquifer. For this case, however, the source groundwater is still quite salty. Because of this, similar treatment would be necessary, and groundwater costing includes drilling as a well and piping infrastructure. These extra costs yielded surface water treatment as the best solution moving forwards.
The second decision matrix served to choose the appropriate desalination technique. 4 different techniques were analyzed: multi-effect distillation, temperature swing solvent extraction, reverse osmosis, and electrodialysis. The largest deciding factor for these techniques was the energy requirements and the cost. Like the water source matrix, evaluation scales were created to assess each criterion with weightings based on the needs of the community. Between the 4 options, ultimately reverse osmosis is much simpler, requires much less energy, takes up very little space, making it the ideal choice for Foundiougn's water treatment system.
Through our design process, we were able to generate a water treatment system that would meet all the design requirements. A simplified model of the system shown on the screen displays the proposed treatment process for the influent water from the Saloum River. In this multi-stage system, the water first travels from the river through an intake screen. Using a pump, the water is then transported to a clear well where chlorine treatment is conducted. From the clear well, the water is then filtered through a dual media filter to further remove small particulates. This water is then transported to a 3-train parallel RO unit using a high-pressure pump. Once gone through the RO unit, the water is then stored in a storage tank until distribution.
Before the water can be desalinated, it must go through a pre-treatment process to remove as many of the other contaminants as possible. This increases the operation lifetime of the reverse osmosis units and reduces membrane fouling. To achieve this, a dual media filtration unit has been designed to target the water's turbidity and hardness. This is done with layers of anthracite and green sand. Anthracite treats for the turbidity while the green sand treats for the hardness. This filter is also capable of removing salt, but for this design the removal is negligible and will be disregarded. At the selected medium depths, turbidity is reduced by 93% and hardness reduced by 99%. Here we have some of the primary operating parameters of the filtration unit. Once per week, the filter undergoes a 15-minute backwash procedure to remove the trapped contaminants and to restore the redox potential of the green sand.
The next process for our treatment plant involves reverse osmosis, RO for short, where the main removal of salt occurs. There is a variety of configurations that provide different results and efficiencies for various situations. Our initial design was for a double-pass RO system, but in calculating a single RO system, it provided acceptable effluent concentrations. Therefore, we opted for a single-stage RO configuration. In calculating the final proposed design mass balance using a provided specification sheet of the selected membrane, a single-stage system results with an effluent flow rate of 37.5 cubic meters per day with a salt concentration of 34.9 milligrams per liter, which is significantly less than the set project constraint. Additionally, the membrane is able to remove other water quality parameters such as turbidity, hardness, and water pathogens. Effluent turbidity and hardness are calculated to be 0.04 NTU and 3.15 milligrams per liter respectively. To demonstrate the design system, a detailed process flow diagram was created to illustrate the 3 single-stage RO system.
In order to operate the treatment and desalination processes with acceptable pressure, 2 pumps were sized. The first of these was a centrifugal pump that is used to collect surface water, and the second was a high-pressure turbine pump that provides the necessary pressure for reverse osmosis. The energy grade line is especially important for demonstrating the energy input and energy consumption requirements of reverse osmosis. The vast majority of the energy provided by pumps is utilized by the RO process, as demonstrated by the energy grade line. This will incur significant monetary cost.
As engineers, it is our greatest interest to provide a water treatment system that will help improve the quality of life of an established community without causing disruption in their daily lives. In order to be considered a successful design, safety protocols had to be incorporated into the design solution. These protocols will help ensure safe operation and the reduction of the possible social and environmental problems that may develop. To ensure the safety of the system's surrounding environment, several precautionary actions were determined. In order to be considered environmentally safe, the intake velocity of the system could not exceed 0.6 meters per second. This was a safety parameter that was followed to reduce the interference of aquatic life. An intake screen was also added to prevent the entrance of any aquatic life or debris into the system. Proper storage procedures of chlorine will be enforced. and training will be provided to ensure known actions if a large chemical spill was to occur. This helps provide protection for the safety of the community and the sharing ecosystems. The waste created from the water treatment process was also considered. This waste will be collected and disposed of in a manner where the environment will not be damaged. The safety of the surrounding society was also heavily explored. This is very important as minimal disturbance of the design towards the surrounding community ensures for a decrease of social stress. Safety precautions were introduced to help provide protection for the surrounding community. The reduction of possible noise pollution was studied and taken into account. This is due to the negative effects that may arise to the community's daily lives. The system will also be built in an area where there are no significant cultural, heritage, or religious significance to reduce potential tension within the community. This also includes the parts of the system located in the water to ensure the local fishing does not receive any negative effects. To ensure the safety of the maintenance workers who will work on the system, numerous amounts of training will be provided. The training will include proper operation methods, hazardous materials handling, and how to monitor the system to ensure the water is being treated to the required water quality standards.
The design solution is intended to service the growing population of Foundiougne for the duration of its anticipated 20-year lifespan. As such, it was necessary to design a treatment process that could provide potable water to the extrapolated population. This is the expected capital expenditure for the project. It is anticipated that construction costs will be approximately 250% of the initial equipment cost.
These are the expected operational maintenance costs for the design project. Note that maintenance is expected to cost approximately 20% of the initial equipment cost each year. The total present value of the project cost was calculated under a series of different scenarios, including varied interest rates and increased capital and operational costs. It can be seen that a 50% increase in capital and operational maintenance costs actually produce a nearly 100% increase in total costs. This is due to the nonlinear effects of revenue and replacement of equipment. These considerations are important because this project is overseas and additional costs may be incurred. In conclusion, this design solution is capable of providing clean and potable water in a cost-effective manner, while also meeting World Health Organization drinking water guidelines. Additionally, this case study demonstrates that, with planning and innovation, potable water can be provided to impoverished communities worldwide.